let's start today by doing a quick review of last time. Last time we defined joint probability mass functions for discrete random variables defined on the same probability space. PMF stands for probability mass function. Joint PMF of two random variables is defined as the probability that the first random variable takes the value x, while the second random variable takes the value y. This is denoted in shorthand notation as pxy x comma y. In the subscript, we write the names of the random variables, x and y. In the argument, there are two values. The first value is the value that the first random variable takes. The second value is the value that the second random variable takes. So this is just a probability. And as long as you get the notation, you understand the notation, it's nothing more than computing probabilities, which you already know about. Okay? So let's see some of the examples that we did. The probability that x and y, the random variables x and y, take values in a set A can be computed, since these are discrete random variables, by taking a summation over all xy pairs in the set A. Okay? Well, a special case for the set A, okay, is the set of ordered pairs in which x is at some value, fixed value, x1, and y is anything. Okay? If we compute the probability of that, we compute nothing but the probability that x takes the value x1. That is called the marginal PMF of x evaluated at x1. So this is the marginal PMF. This is the first PMF, the probability mass function that we defined. Px of x is the probability that the random variable x takes the value script x. Okay? Now, this can be computed by taking a union over all x and y, over all y, okay, of the events x equals x while y is y, okay, and computing the probability of this thing. Okay, this boils down to a summation. Why? Because probabilities are additive when the underlying sets are disjoint, which these are. Okay, summation over y, px equals x, y equals y. So summation over y of the joint PMF gives us the marginal PMF. Okay? So this is py of y. Similarly, the marginal of y. The marginal of y can be found by summing over all x, summing along the x direction, okay, pxy, the joint PMF. Okay? We looked at this example, if you remember. Let's quickly go over this example. This table tabulates the joint PMF. Okay, so for example, this value is the probability that x is 2 while y is 1. Okay? Now from this, we computed the probability that, let's see, x is less than y. Okay? Let's compute it again. Okay? The probability that x is less than y. The event x less than y includes 3 outcomes in this case. Here, x is 1 and y is 2, so x is less than 1. This happens with probability 1 over 10. X is 1 while y is 3. X is 2 while y is 3. These 3 together make up the only possible cases where x is less than y. Sum their probabilities 1 over 10 plus 2 over 10 plus 2 over 10. 5 over 10 is the probability that x is less than y. Okay? So this is how we use the joint PMF to compute probabilities about the random variables, to compute the probabilities of events such as x is less than y. What is the probability that x is more than y? Anybody? X is more than y would be the opposite triangle, on the opposite side of the diagonal, right? This is the diagonal where x is equal to. Huh? Let's see, 1 over 10 plus 2 over 10 plus 1 over 30. So 3 plus 6 plus 1, 10 over 30. 1 over 3. Okay, that's the probability x is bigger than y. Okay, any questions about this? So now everybody knows what a PMF is. What does PMF stand for? Probability mass function. What's joint PMF? The joint probability mass function of two random variables. Okay, and how do we get from the joint to the marginal? For example, let's find the marginal PMF of x. The marginal PMF of x is a function, remember. It's a function. So we need to compute it at every possible value that x can take. At x equals 1, what is the probability that x equals 1? 1 over 10 plus 2 over 10, 3 over 10, 0.3. Okay, that's the that's px of 1. Px of 2 is the sum of this column, 1 over 10 plus 1 over 15 plus 2 over 10. Px of 3 is this the sum of this column. On the other hand, Py of 1 is the sum of this row. Py of 2 is the sum of this row. Py of 3 is the sum of this row. Okay? Any problem? Okay, so everybody's now following. Great. Let's quickly go over a few other things that we did last time. It was easy to convince ourselves that a PMF, joint PMF, when you add the values over the whole region of x and y, should add to 1. Okay, so we use that fact to determine the C here. Okay, x and y were jointly distributed in a triangular area. In fact, they took 3 possible values, I believe, right? And they took those values equally probably. They took those points equally probably. So we determined C to be 1 over 3 so that the PMF would sum to 1. Okay? And we found the marginals. Remember, the marginals were like, taking a cut across the joint. Okay, so, and then we looked at functions of two random variables. Okay, a function of one random variable is a random variable. So by extension, a function of two random variables is also a random variable. In fact, a function of any number of random variables defined on the same sample space is another random variable. Okay? We can find the distribution, the PMF of this new random variable simply by summing the PMF, the joint PMF of the original random variables over the region where the ordered pairs map under function g to the value z. That would give us the PMF of z at the value z, small z. Okay? What else? Expected value. The expected value rule extends to this case. Expected value of a function of x and y can be found by taking the values of the function weighing them by the probability masses, okay, and summing over all x and y. Okay, again, a weighted sum, nothing but a weighted sum. Okay, when G is linear, since expectation is linear, we can change the order of this linear combination and expectation. So expected value of ax plus by plus c is nothing but a times expectation of x plus the b times expectation of y plus expectation of c. But what is the expectation of c? C itself. Expectation of a constant is constant, the constant itself. We use this as a trick to compute the expectation of the binomial, because what is a binomial random variable? A sum of Bernoullis, right. Binomial random variable comes with two parameters. What are they? The number of trials and the probability of success in each trial. Okay, so I can write a binomial random variable x as the sum of n individual identically distributed Bernoulli random variables, x1 plus x2 plus xn. So the expectation of x is the sum of the expectations, but the expectations are all equal to p, because why? The expectation of a Bernoulli random variable with parameter p is just p. Okay, so the expectation of a binomial with parameters n and p is n times p. Okay. The hat problem. Let's revisit the hat problem real quickly. I kind of changed the wording after class. Let's consider this wording, because some people were not happy about exactly what the rules of the game were in the hat problem. So think of the following. Consider a string of length n randomly formed by shuffling the string 1, 2, 3, 4 up to n. Let's write this down. Okay. So for example, let n be equal to 7. Okay, our string is formed by shuffling 1, 2, 3, 4, 5, 6, 7. Okay. So every ordering, every permutation of this string is equally likely. So I shuffled it, for example. What did I leave out? 6. Good. So I got this. Okay. Now let's see how many letters are in the same places as they originally were. In this case, none. Okay. But for example, if it was like this, 6 is, after the random shuffling, 6 ended up in its own original place. Okay. So, let's see. Okay. Now, with this wording, answer the following question. What is the probability that after the shuffling, a number ends up in its original place? There are 7 possible locations. Okay. 7 possible locations. There's total symmetry. For each number, it should be the same probability. There are 7 locations to choose from. Each are equally likely. So 1 over 7 is the probability a number ends up in the same place as it started, right? So in general, let xi be equal to 1 if number I ends up in location I. Just one. I'm talking about just one. What is the probability that 6 ends up in the 6th location? What is the probability that 3 ends up in the 3rd location? They are 1 over 7, right? So let xi be 1 if the number I ends up in location I, okay? And 0 if it does not, okay? So xi is the indicator function of the event that number I, after the shuffling, is still in location I, okay? The xi's have the same distribution for each I. Does everybody agree that this is true? Okay. Yes, please. Right. So x3, okay, x3 is concerned with only the number 3. x3 is 1 if the number 3 falls into the 3rd location, and 0 otherwise. What is the probability that x3 is 1? 1 over 7. So in general, 1 over n, if there are n numbers, right? So xi is 1 with probability 1 over n, and 0 with probability 1 minus 1 over n. Is xi Bernoulli? Yes, by it fits with the definition of the Bernoulli random variable. Okay, so what is the expectation of xi? The parameter, which is the probability of xi being 1, which is 1 over n. 1 over n. Now the next thing to notice in this example was, what are we looking for? We are looking for the number of the total number of integers staying in their original locations, and we're looking for only the expected value of this number. Okay? Now the number of numerals ending up in their original locations is nothing but summation xi, I from 1 to n, right? Because it just counts. When we add x1 and x2 and x3, it just counts the number of numbers whose locations don't change. Okay? So we are interested in the expectation of this quantity. This is the expected value of a sum of random variables. Expectation of the sum of a number of random variables is equal to the sum of the expectations. Okay, but for each I, any question? Okay, for each I, the expectation is 1 over n. So this sum is n times 1 over n, which is 1. Okay, are there any questions? Where? Now, xi is a Bernoulli random variable with parameter, what is p? Of xi being 1 is, in this case, 1 over n. Okay, let's compute this. Let's write this. Let's write a computation for this. expected value of xi is 1 times the probability that xi takes the value 1, which is 1 over n, plus 0 times 1 minus 1 over n. Right? So 1 over n. Right? Okay. So any questions about the hat problem? Yes, please. Excuse me? We have found the expected value of the total number of numbers whose locations don't change. We already did that.
Hocam,
Yes.
bir şey soracağım. Burada bir şey oynasaydık mesela, iddiaya girseydik, 1, 2, 3, 4 tane aynı location'a girecektik. Buna 1 dememiz bizim için daha mı yararlı oluyor şimdi?
I don't understand your question. Can you repeat that?
Mesela 7 tane location var ya, 7 tanesinin de aynı yere gelme olasılığı. Buna iddiaya giriyoruz. Mesela 1 diyebiliyoruz, 2 diyebiliyoruz, 3 diyebiliyoruz, 4 diyebiliyoruz gibi. Şimdi burada expectation'ı 1 bulduk ya. Bu bizim 1 dememiz bu iddia sonucunda daha mı iyi oluyor? Daha mı şey oluyor?
Well, okay. That kind of betting mechanism, how profitable it is, depends on what you bet. Okay, how much you are willing to lose if you lose the bet, and how much you are going to get if you win the bet. So your strategy and your expected gain depends on, more rules of the game to be specified. The expectation is just expectation. This is right. I mean, later on, we'll also compute the second order statistic in this problem. In fact, we'll compute the variance of the number of numbers that end up in their own location. Expectation can sometimes be very misleading. In the future, in this class, I'll give you examples where the random variables actually converging to infinity, a sequence of random variables that are converging to infinity, while their expectation is constant at 1. Or expectation is going to infinity while the numbers are not. Yes, please. Exactly. Even if there are, this is an interesting example because this expectation comes out to be independent of the total number of things we are shuffling. Right. Okay. So that was last time. The new topic for today is conditioning a random variable on an event. Okay? The conditional PMF, the conditional probability mass function of the random variable x, conditioned on an event A, whose probability is different from 0, is defined by Px given A, okay, which is the probability that x is equal to x given that event A happened. Okay. In other words, using the definition of conditional probability, this is the probability that x is equal to x and A happens divided by the probability of A. Okay. So I think this will be really clear after doing some examples. First of all, we need to believe that Px given A is a legitimate PMF. What do I mean by a legitimate PMF? It has to sum to 1. Okay, let's just show that this Px given A, so show that summation over all values of x, Px given A, x given A, sums to, is equal to 1. Okay? Now, Px given A, what is it a function of? It's a function of how many things? How many parameters? Just one parameter. Okay? This tells you that given A happened, what is the new probability mass function of A? Okay, let's do this example first, and then we can worry about this. Just to get to understand notation, it's going to be useful to do this example first. Okay. Now, you all remember what a tetrahedral die is. A die with 4 faces. 1, 2, 3, 4. They are all equally likely. Okay. Let X be the outcome of the die roll. Okay. What is the PMF of X? PMF of X is 1 over 4 at the values 1, 2, 3, and 4, and 0 everywhere else. Okay, so X is the result of a tetrahedral die roll. Okay, Px of X is equal to 1 over 4 when X is 1, 2, 3, or 4, okay, and 0 otherwise. Okay, any problem? No. So now we are given that the die roll did not result in a 1. Okay. Now, how likely is the value 1? Its probability is 0. How likely is the value 2? 1 over 3. So that's the idea. It's quite intuitive because you already know what conditional probabilities are. Okay, A is the event that outcome is not 1. Okay, what is the probability of A? 3/4, right? Now, we are asked to compute the PMF of X conditioned on the event A. Okay? And by definition, this is the probability that X is equal to X and A happens divided by the probability of A. Now, what is this probability that X is equal to X and X is not 1? For all values other than 1, X is equal to X and X is not 1 is nothing but X is equal to X. So this is equal to the probability that X is equal to X divided by the probability of A if X is not 1. X is not 1. In other words, X is in the event A. And 0 otherwise. Okay? So 0 if X is 1. So let's compute this. The probability that X is equal to X is 1 over 4. P of A is 3/4. So this is equal to 1 over 4 divided by 3 over 4 if X is, which is equal to 1 over 3, if X is 2, 3, or 4, and 0 if it's just 0 otherwise. Okay? So we computed the conditional PMF of X conditioned on the event A. Okay? So let's plot the original PMF and the conditional PMF. The original PMF had took equal values at 1, 2, 3, and 4. The equals were the equal value was 1/4. This is Px of x. And Px given a, x given a, now it takes values only at 2, 3, and 4. The heights are 1/3. Okay. So what has happened? Let's look at this versus this. Okay. I claim that the original PMF has just been limited to the to consist only of the values included in the event A, okay, and the values have been renormalized so that the PMF will be a legitimate PMF. Okay, so what this thing is doing in the denominator is normalizing. Okay, normalizing the fractions such that they will sum to 1 over a more restricted range of values. Okay. Now that we restricted the values, the possible values to 2, 3, and 4, we need to rescale the probabilities such that they'll sum to 1. Okay. Okay. So now let's show this formally. Okay, let's formally show that the normalization is successful. Okay, how do we do this? The hint says use the total probability theorem. We can use the total probability theorem to express the probability of A as a sum over all values of x, probability that A, probability of A intersection x equals x. Okay. A intersection x equals x for different values of x are disjoint sets, and when we take the union of them, they completely cover A. Okay, so this is the total probability theorem because these are a partition of the event A. Okay, this is nothing but, A happens if and only if, A and one of the x equals x events happen. Okay, so now let's write Px given A again. Px given A, x given A, is the probability that x equals x given intersection A divided by the probability of A. Okay, and we are supposed to sum this over all x. And so let's sum both the right-hand side and the left-hand side over x. P of A is a constant. It comes out of the summation. So we have 1 over P of A times summation P x equals x and A. Okay, over all x. But what is this expression? It's nothing but P of A. Okay, so this is P of A divided by P of A, which is 1. Okay, so now we, really showed that normalization holds. So this scaling dividing by the probability of event A is just to normalize the PMF. Okay, so going from a PMF to a conditional PMF, let me repeat. You just take the PMF, restrict it to the event A, okay, and then normalize. That's it. It's very simple. Okay, any questions? Next, we have a really fun example coming up, but I want to make sure everybody is fine with the definition of conditional PMF before we move on to that example. Any questions? Yes, please. Excuse me? Now, X is the result of the die roll. X is either 1 or 2 or 3 or 4. But if we know that it's not 1, then it can only be 2, 3, or 4. Okay? And 2, 3, and 4 are now equally likely as they were before, but their probabilities rose to 1/3 from 1/4. Okay, any other questions? Let's at least start, take an attempt at the next problem in the amount of time that we have remaining, because I believe it's a really fun and educational example. Okay, my friend Ali will take the motorcycle test again and again until he passes. Okay. Each time he takes the test, the probability that he passes the test is P, irrespective of what happened in his previous attempts. But the problem is he's only allowed n attempts to take the test. Okay, so if he does not pass any of his first n attempts, he will have to quit, okay, without getting his license. Okay, the question is, what is the PMF of the number of times Ali takes the test? Okay, so let X be the number of attempts at the test, meaning number of times he takes the test. It's a random variable, right? What values does it take? Huh? 1 up to n. Okay. When is it 1? What is the probability that X is 1? He passes at his first trial. That happens with probability P. Okay, he passes his first attempt and he takes his license and stops. Okay. If he doesn't pass the first test, he will take it again. If he takes it again and he passes, then the total number of attempts is 2. What is the probability of that? Great. 1 minus P times P. So what is the probability that he takes the test 3 times? 1 minus P squared times P. What is the probability that he takes the test n minus 1 times? 1 minus P to the n minus 2 times P. What is the probability that he takes the test n times? Now, n is a little different because he will quit for 2 reasons. If he failed his first n minus 1 attempts and passes the nth time, he will win and stop. But if he fails for the nth time, he will again have to stop because he reached his limit. Okay, so the probability that he stops after n trials is the probability of winning on the nth attempt plus the probability of not winning at all, not getting the license at all. Okay, so, well, what is the probability of this? 1 minus p over n minus 1. Clever. Why? Because if he fails the first n minus 1 tests, the total number of tests will be n regardless of what happens on the nth test. So, you know, he failed the first n minus 1 tests. The morning that he's getting ready to go to the nth test, he says, well, I tried. This is my last test. Whatever happens, it's it. This is it. Okay? I'll either pass or fail. This is my last test today. So, you know, I'll go and celebrate today. Okay? Okay. So, okay, any problem with this? Alternatively, we could have computed this using 1 minus p to the n minus 1 times p plus what? 1 minus p to the n minus 1 times 1 minus p, which is 1 minus p to the n. Okay? So this is the probability that he passes on his last chance. This is the probability that he fails entirely. Okay, and if you sum these two, you know, take the whole thing into 1 minus p to the n minus 1 parenthesis, so, you know, you see that it's equal to this. Okay, we found the PMF of the number of attempts in general. Now, let's find the PMF of the number of attempts given that he passes. By the way, let's plot this. It's always nice to try to plot a PMF when you've computed it. So this is 0. 0 is not possible. Negative values are not possible. At 1, the probability that it's 1 is p, px of x. The probability that it's 2 is like this. Probability is 3 is like this. And up to n. And after n, it's 0 again. Okay? Okay. Now, A is the event that Ali eventually gets his license. Okay? So, he passes. Okay? What is the PMF of the number of attempts, x, given that he passes? Okay? P, x given A, x given A. Okay. Remember, we just limit to values that are possible, values of x that are possible when event A happens, and then normalize. Given that Ali passed, what values are possible for the number of tests taken? All values. Right? All values are possible. Okay? So, the probability that x equals x and A divided by the probability of A will be computed for x from 1 to n. Okay. Now, for what is the probability of A, by the way? P of A. The probability that it does not fail eventually. The probability that he does not end up failing all n attempts. Okay. 1 minus the probability of failing all n attempts. Okay. So, now, what is the probability that x is 1 and he passes? Well, if x is 1, he passed. So it's the probability that x is 1, p. P divided by p of a. Let's write it here. 1 minus p to the n. Okay, if x is 1. Similarly, it's 1 minus p times p divided by 1 minus p to the n if x is 2. Up to what? Up to n minus 1. Okay. So the probability that number of attempts at n minus 1 given that he passed is 1 minus p to the n minus 2 times p divided by 1 minus p to the n. Okay? Now what happens to the last probability mass? The first n minus 1 probability masses have been scaled up by the same amount, by the same coefficient, that is, by the same factor, that is. Okay. So let's compute px given a, x equals n given a. This, okay, this probability, the probability that x is n and he passes, is what? He fails the first n minus 1 attempts and he passes the nth test. We don't have the other thing, other part of the summation, divided by 1 minus p to the n. Okay. All right. Any questions? So we've computed the conditional PMF of x given a. Of course, px given a is 0 for all other values other than we've written. Think about this. I'd like you to think about this example, and we can go over it again and go over your questions next time. Okay? So have a nice week.